Yeah, good morning. Myself, Praparanjay, working as an assistant professor in EC department at SNS College of Technology. In this lecture video, I am going to talk about the topic is MOS non-idle current voltage IV characteristics from the unit 1, which is MOS transistor principle of the subject name is VLSI design. Let discuss. Yeah, these all are the topics to be covered by this lecture video. Okay, we will discuss one by one. Okay, first one is transistor current voltage characteristics review. Ideal review behavior. Okay, first one is we know the region of the transistor, cutoff region, linear region, saturation region. Ideal behavior of the transistor is for the cutoff region, that is voltage is VGS less than VTH, IDS equal to 0, which means minimal current flow at the cutoff region, and another one is linear region, IDS equal to beta into VGS minus VT minus VDS divided by 2 into VDS, where drain source voltage lesser or equal to VD saturation at the linear region. In the linear region, the linear relationship between current, drain source current and drain source voltage. And another one is saturation region. Here VGS greater than VTH and VDS greater than VGS minus VTH. Here current, drain source current relatively independent to drain source voltage. IDS equal to beta divided by 2 VGS minus VT whole squared, where VDS greater than or equal to VD saturation at the saturation region. And let me discuss the non-ideal transistor behavior. And first one is velocity saturation. At high electric field, carrier velocity saturate due to scattering mechanism, and the effect of this is limit maximum current, affect high speed operation, and reduce overall device efficiency. Here we assumed carrier velocity is proportional to the electric field, that is the carrier velocity V equal to carrier mobility M into lateral electric field E lateral, which is equal to the M into VDS divided by L. At high electric field, this is ceases to be true. Okay, velocity reaches V saturation. Velocity reaches the saturation voltage. Electron, which are a charge carrier in NMOS transistor, have a saturation velocity in the range of 6 to 10 million centimeter per second. This means that even if the electric field increases, the electron's velocity will not significantly exceed these ranges. And another one is holes, which are the charge carriers in PMOS transistor, have a slightly lower saturation velocity in the range of 4 to 8 million centimeter per second. The saturation velocity is a fundamental property of the semiconductor material that limit the maximum speed at which a charge carrier can move through the MOSFET channel. Designer must account for this limit when optimizing MOSFET performance in high speed and high power applications. Okay, velocity saturation, current voltage effect. Ideal transistor on, current increases with VT squared. Here you can see the equation, drain source current. And velocity saturated on, V set on, current increases with VDD. IDS equal to some equation, IDS equal to COXW into VGS minus VT into V maximum. Okay. Power model. Okay. Channel length modulation. As drain source voltage increases, electric field effect cause the effective channel length to shorten near the drain. L is nothing but the length of the channel. The effect is I d suffix ds depends on the v suffix ds. That means drain source current depends the drain source voltage in saturation affect output impedance and gain. Next is body effect. That means saturate bias effect. Variation in substrate bias alter the effective threshold voltage VTH. Effect of this is shift Thevenin affect transistor operation and circuit design robustness. Off transistor behavior. When a transistor is off, an NMOS transistor has gate source voltage less than threshold voltage. PMOS transistor has source gate voltage less than threshold voltage. Okay. Both types of transistor, which means NMOS and PMOS, present in high impedance and ideally don't conduct current between the drain and source terminal. Small leakage current may still be present due to various physical effects. Understanding the off-state behavior of transistor is crucial for designing efficient and reliable CMOS transistor. A leakage current can affect power consumption and overall circuit performance. Leakage. Various mechanism like gate induced drain leakage, drain junction leakage, subthreshold leakage, which increases of state leakage current, impact power consumption and reduce battery life in low power application. Leakage current in MOSFET are non-ideal behavior and deviate from the ideal current voltage characteristics. These leakage current can significantly affect the performance and power consumption of MOS circuit, especially in low power, high density application. Here, some of the leakages, subthreshold conduction, transistor can't appropriately turn on or turn off, and another leakage is junction leakage, and the third one is gate leakage. Subthreshold leakage is the biggest source in modern transistor. It occurs when the transistor is supposed to be off. However, due to the thermal energy, some carriers can still diffuse from the source to the drain. IV characteristics. This leakage current is exponential with respect to the gate to source voltage and inversely proportional to the thermal voltage. It becomes significantly in short channel devices. Okay, subthreshold voltage leakage exponential with VGS. And drain induced barrier lowering. In short channel MOSFET, the electric field from the drain can lower the barrier for carrier injection from the source to the channel, causing increased off-state current. IV characteristic DIBL, which means drain induced barrier lowering, manifest as an increase in off-state current and a reduction in threshold voltage with increasing drain voltage. Junction leakage occurs due to the reverse bias leakage current across the source drain to body junction. Let me see the IV characteristics. This junction leakage current is temperature dependent and increases with higher doping concentrations and higher reverse bias voltage. And another one is gate leakage. It occurs due to the high electric field near the drain region when a high drain voltage is applied, leading to band-to-band tunneling and carrier generation. This leakage is prominent at high drain voltages and low gate voltages and shows up as a leakage current in the off state. Next is temperature leakage. Temperature sensitivity. Changes in carrier mobility, threshold voltage and leakage current with temperature variation, which alters if transistor performance characteristics require thermal management in circuit design. Next one is parameter variation. In MOSFET is refers to the deviation in device parameters from their nominal values due to manufacturing process variation, environmental factors and aging factors. These variation can impact the performance, reliability and yield of integrated circuits. Environmental variation, which impact on MOSFET. Temperature variation. Yep, as previously discussed, temperature variation can affect threshold voltage, carrier mobility, subthreshold slopes, leakage current, and overall performance. Use thermal management techniques like heat sink, temperature compensation circuit, and ensuring adequate ventilation. Similarly, supply voltage variation, which is the environmental variation, and electromagnetic interference, humidity and moisture, mechanical stress, radiation, likewise. Next one is process corner. Represent extreme variation in process parameter, which effect designer must account for worst case scenario to ensure circuit reliability across process variation. This is the assessment for the this lecture video. If you have any doubt, means you can ask me through the comment. We will meet in next video. Thank you.